Hi, good morning. It took me a while to get started here, but here we go. Great. We have a lot of symptoms coming down the pipe for this COVID-19, and we want to review some of those and how they've changed. This virus is mutating. That's what things that survive do. Survival of the fittest, and that goes for viruses too. So what is this virus? CDC, the Center for Disease Control, is saying we're not sure if it's a living or non-living thing. Well, where have we heard that before? Bacteria. We know a lot we've heard a lot about bacteria. It's one of the first things we discovered as scientists. They're all over the place. They've got weird forms. Yeah, it's pretty well accepted they're alive, right? Bacteria are alive. Enter Gallionella. Gallionella. Metals-based bacteria. We've been talking about that. Gallionella. It's a metals base. Are metals alive? We have metals in us, transition metals. I studied them in Jane Flint's lab for years, looking at copper, iron, zinc, other elements that play into development of Alzheimer's plaques. So metals-based bacteria. We've got Gallionella. You've got a pipe that water's flowing out of, and there's an iron ore mine upstream from it, and it's getting iron out of bedrock, buried iron that's been buried, prehistoric, Jurassic iron, let's call it. You got to look at the interplay of these irons in biological development. And so there's iron. And what do they use to get the iron out of the bedrock? Manganese. And what do they use with the manganese? They add it with water, H2O. So then that creates a bacteria that pretty much looks like and explains our mitochondria. Okay, so way back when all this iron, this is, let's say, 10 million years ago, and the dinosaurs had kind of plopped off and whatever. We can look at dinosaurs another day. Super duper bodies and teeny tiny brains and hearts and lungs. So it's relative. It's relative to, as far as I can tell, to the amount of metals that are floating around the environment. We can look at that. We'll look at Northeast Brazil. Let's put Northeast Brazil in the middle of this. NE Brazil. And they had a water supply that came from one of these gluttonous, nonstop, producing more than it should have been, about like this, and they were doing this as far as iron ore unearthing and spewing into the environment and dumping their waste recklessly and no oversight. And what do you get? You get a normal child's brain is kind of like this, right? Eyeball there. Hi, I'm a happy kid. To a compressed skull that has a shelf on it, and you've got a very severely limited child, kind of like a caveman with a supersized body. Supersized ears, supersized body. And they're very responsive to music too. How good is that? Sweet, yay. But it's like they are all, 1 million years ago, humans. This is Northeast Brazil. So let's just look at that later. And Zika is flying around everywhere, and it does get into the brain for reasons, but it's not causal. I don't see it as causal. That's obvious. Zika Shmika, come on. Okay, so we all know that by now. But why? Because of the metals that are being iron, manganese, which do not belong in first trimester. We've talked about that. Iron does not belong in first trimester. Women become anemic, let them become anemic. Doctors, stop giving them iron. May be causal to things like autism, things like that. So, let nature take its course unless it's killing us, right? Okay, so 10 million years ago, there was upheaval, mountains all over the place, going on volcanoes, whatever, God knows. And there was a lot more iron. This iron is buried now. This iron is buried. There was a lot more iron, and manganese is a flake, so that's all over the place. And of course, we had lots and lots of water. And the oxygen levels of the planet, because of aerobic bacteria, were going up, 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 up. So when they went up, that's when we came out and became humans. All this oxygen has fueled dynamic processes that help us to grow and grow and grow and grow and grow. From a single cell organism, eukaryotic cell, on the same phylogenetic tree as the mushroom, to multicellular nematodes, worms, a lot of marine plankton type base. So, and then how we continue to evolve is sometimes these things co-localize. And so that seems to be what happened. I'm boring you out with this blue here. So this multicellular organism that came out of this, let's say post-Jurassic, post-dinosaur period. And we have to look at what led up to the dinosaurs and all of this, whatever, iron and such. And who knows, the big cataclysmic crater comet or blast that killed the dinosaurs may have also buried all of this iron that fed into super-size ooga booga looga booga dinosaurs. And you see that in Northeast Brazil. There's so much iron. This is in Northeast Brazil. There's so much iron that has been unearthed and into their water system that you're getting these teeny tiny heads, Jurassic little, and supersized bodies. Getting supersized bodies in these children. So what we've said in the past is that first trimester gestation for us is a very protected thing. And when you're kicking back iron and toxic drinking water, and we don't need that. We're not supposed to have that during gestation naturally as evolved humans. So industrialization, INDUSTRY, industrialization has, can't get enough of iron unearthing, steel, deforestation, destroying the oxygen supply. It's got to stop. It's got to stop, or life as we know it is not going to continue. So let's look at these symptoms. That's what I meant to talk about today, and I want to talk about today. Because at first they kind of started out pretty innocuously, and I think that's all that doctors could really pinpoint on. And as with any disease, you're going to have a variety of symptoms, and as the more numbers come in, the more it kind of narrows down. So headaches, fever, and a light cough. This was a doctor in Paris, Sylvie Monnuet. And then they added a runny nose and a scratchy throat. By the time we got it, it was a dry cough, right? Dry cough, fever, and that's it. And no symptoms. That's how I remember getting to it and it coming to me. Then as weeks went by, and we've been talking about this for weeks too, that skin lesions, that will be a low zinc. So we have to look at what happens to zinc. We've looked at that in past things. Neurological problems, a lot of hallucinations, And in this process, I've been able to look at mitochondria and understand much better, their cycle. We have a cycle. We're awake and conscious during the day. We can get a lot of stuff done, enjoy it, be sensory responsive, enjoy blah, blah, blah. Well, where are the mitochondria? They're buried deep inside, right? In all of our cells. They have a life too. They have their own DNA. And so when do they have their party? I believe it's during the sleep state. I believe that we kind of reverse. There's so many dichotomous aspects of it. So what happens in our conscious state may be on almost more of an automatic pilot for the mitochondria, including production of reactive oxygen species. And then what do we know about that? We were talking about the, oh gosh, let me write this down because it's a beautiful thing. So oxygen comes in here during the day, it just diffuses around. We don't have to work to get it unless we breathe more. And try to, overcome all the industrialized stress and triggers and fear and regression that it triggers. It triggers a lot of regression. Grab it. And an electron is donated here. So O2 comes in. I thought it came in missing one. And so it's donated here. And I know iron has an extra electron at one point. And I'm not sure where that electron comes from at this point. These things are it's amazing they've figured these things out. So that becomes what is this hydrogen peroxide, which is toxic. This is when there's low oxygen, the body knows something's going on. And in the process of adding this electron, it gets this superoxide. And so this can go become this hydrogen peroxide if things get bad enough. Trust me, they get bad enough. Doctors know all about the disease. They all know all about this cascade. What they don't pay as much attention to is what happens if we just get enough oxygen. If we just get enough oxygen, none of this has to happen. That's the 2019 Nobel Peace Prize. This is all a result of hypoxia. Everything beyond our oxygen, yay, bada bada boom, stay oxygenated. A little bit of hydrogen peroxide is great. But if you're a happy hypoxic, this is all you're getting is hydrogen peroxide, and that's just destroying everything. So what mediates this, what turns this super oxide, that makes sense because when oxygen, okay, I'm with you here. I'm getting back here because I'm having to do it from the causal aspect. O2 does have a missing electron, yes. Whether it comes from this extra one in iron, that makes sense. Iron brings oxygen here, offloads an electron. That electron turns this into oxygen. They call it O2 because there are two oxygens together, but it's missing an electron when it gets to the mitochondria. It gets an electron, and that enables it to split and continue to oxygenate. It becomes just O. Yeah. And from that, we get all this ATP. Yay! From the mitochondria. Now, if there's not enough oxygen, these electrons build up, and there are protons released. For every electron, there's a proton. So it's all kind of paired and matched. This is toxic. I had this at the dentist the other day. They put hydrogen peroxide in my mouth. It was really gross, and it kept kind of foaming and and just over about 2.5 minutes, I had to spit out about 4 times. I thought it was gone, then I just kept going and going. So it's very reactive. So, okay, and what mediates this is superoxide dismutase. So here's the superoxide. It comes in as oxygen with a missing electron. An electron is donated to make it oxygen with, both of them. That's how they nomenclature there. And then this can go in two directions. It can go toxic if it's hypoxic, or it can go oxic if it's supported by by the processes in the electron transport chain. I don't know. It doesn't make all that. I mean, this is complicated science, but the bottom line is we need oxygen to optimize. Proxic, ultraoxic. So these symptoms we're getting fold into a lot of that. There's so much amazing stuff. There's some work on NADPH this morning that came in that, again, where there's causation, all you find is evidence. So all the good things are supported by oxygenated processes that we can control. We're not going to do it automatically. Why? Because we're full of fear, anxiety, stress, horns blowing. We're surrounded by plastic. But mindful meditation, yoga, breathing exercises, just the basic understanding. Breath first, and all else follows. That's amazing. Okay, so this superoxide dismutase is what is most important about this. Gee, this is like the climax of the show here, folks. Pay attention. Is iron, manganese, and copper. So copper goes a lot of places. Remember, copper's in first trimester, and then it kind of slips over here and just not as important, but it goes a lot of places, and it orchestrates. It's like the driver. It's like the Lyft drivers all over town, taking everybody everywhere, making sure everybody gets there, making sure da-da-da-da-da-da. That's copper. That's copper. This is copper. Cu, copper. And copper is in this superoxide dismutase that can take it to toxic. The cell will protect itself, or the cell will just keep growing. The cell will protect itself with this H2O2. Sorry, I'm pointing the wrong place. H2O2, or it will keep growing with oxygen. H2O2, oxygen, right? So there's a turning point in this mitochondria, in this electron transport chain that produces our energy. And iron, manganese, and copper. Okay, so all right, we're working up I'm filling up a board here, but okay, so copper is busy, all the in our health and cellular activity and DNA and RNA and PTA and GSA, Gerontological Society of America, all of our A's. It's busy. It makes it all happen, including protective stuff, including, it's like the Lyft drivers. It takes people to the army bases, and it takes them to the hospitals, and it takes them to the, it makes the cell work optimally. This copper is very important in the DNA God. It's so important that when these blood clots are due to, it fixes the wounds. It fixes the wounds. And when there's too much copper, there's too much fixin', and there's blood clots. We need to look at that. We need to understand that our lack of oxygen from this disease, and on a regular basis, this lack of oxygen on a regular basis has mutated our mitochondria, has messed our mitochondria up. Over time, progressive. Remember the whale? Progressive, systematic. And our mitochondria, which are usually like bean shape, you get rid of the oxygen supply, and it relies more and more on the crisis mode. It starts to misshape. And it even gets so bad that it gets in kind of like, oh my God, I'm barely surviving here. You take off more oxygen, and that's what you get. And when you get here, when it gets to this point, these beings who are in the cell by the hundreds and thousands, they say, okay, we're not raising the red flag we're going to sacrifice. And at that point, while copper is, let's go back down here a little bit, while copper is busy, zinc, I'm surprised zinc's not in here. Zinc is locked away in like banks, zinc banks. Let's call it the bank. All locked and tight, just like all these people in the world who have all this money. Lock it away. Don't live, just lock it away. So, that was a bad comment, but yeah, ball and chain. So once it gets to this, it says, let go of the zinc because we are going down. We are shutting this cell down. And from my understanding, one mitochondria can make that decision. You know, if a mitochondria gets that bad, I am so sick, we have to shut this down. Shut down this cell, and the cell gets shut down, more cells get shut down, the networks get shut down, you get heart disease, lung disease, all those things. Okay, and of course manganese, what does manganese do in this? If there's no oxygen, what's manganese going to do? That's a test question. What does manganese do? Water, let's look at the water molecule, right? H2O, what does manganese do? It splits it. It splits it. I don't think it splits H2O2. I don't think it can split H2O2. It might. But I know it splits H2O. Boom, it can do that. And what happens when you do that? You get oxygen to the mitochondria through fluid, not through lungs, through fluid. It does that for fish, does that for plants, and it does that for us. All right, so let's look at some more of these symptoms. I'm trying to get to the point. I'm trying to review what we've done. And if all goes well, And if all goes well, if this cycle continues, this H2O2, this is very interesting, and I don't think scientists have made this connection. But let's make it right now. This is new science right now. You're on it. Because I thought, well, how is this possible that the mitochondria go through these? Okay, so what happens when you're in hypoxia? So the oxygen comes in, O2 with that missing electron, right? With a missing electron. That electron is donated, I would say, if it's not, I'd be surprised, from the Fe3, because I know it offloads an electron, gets it here, and then slips away to go get some more oxygen from the lungs. So this oxygen becomes a superoxide, or it becomes, it becomes more reactive. And it's ready to either, to work for the cell, to either come back, be divided when there's more oxygen, when there's oxygen, plenty of it, or what little oxygen makes it to these areas of the brain. And the hippocampus is the last drop-off point for oxygen in the brain. That's why Alzheimer's starts there. Because if a little bit of oxygen gets to the brain and there's not more coming, it can either, then this is not going to happen. And we're not going to have all this ATP. This is the ATP party, right? ATP. But let's assume there's no oxygen. So this does not turn into, big time ATP. Rather, we get hydrogen peroxide. It's like whatever's making us stop breathing or slow down, we got to go after it. And that is part of the immune system. This is the immune system. Or items. And then as the protons build up, yes, it does split. It says OH. So we get more of the protons going there. And there's several things that go on in here that are reversible and irreversible and such. Another electron is donated. They're coming and going here. Electrons are being, added to this whole, added, more electrons added, from my understanding. This is Dr. Holt's diagram. And finally, it turns back into water. So basically, what I see here, and this is really important because I don't think they realize this. I'm not sure if scientists realize this, that what the mitochondria is doing is feeding on itself pretty much. We don't have the oxygen coming through the lungs, right? And all of this is happening in the mitochondria. Oh boy. This where there's causation, all you keep finding is evidence. I tell you, it's a wonderful world of science. And I'm standing on the shoulders of giants. So here's our one. An oxygen cell happens to make it to the hippocampus. Well, does it get turned into ATP? No, it gets turned into, oh my God, let's kill what's causing the problem here. Here's more of the problem, and we've done everything we could. We're exhausted. We'll thank God we know how to make a water molecule. H2O. So, in light of hypoxia, as far as I can tell, oh my God, H2O is produced. Okay. So when this mitochondria is in distress, when there's a stroke or a concussion, or let's say stroke or concussion, where there's flooding, there's too much blood running loose, and it's not getting back to the lungs to oxygenate, so that it's running out of oxygen. That it's being flooded, and there's no oxygen in the blood anymore, and the mitochondria start to panic because they kind of feed on oxygen. So what do mitochondria do if there's a stroke? People don't really follow this, but it's out there. There's science is there. It's pretty clear. So you got hit on the field. You got a stroke, and then it starts to bleed. And you'll see something happen on the edge of that bleeding, and then it'll bleed some more, and there's something happening on the edge of that bleeding. Wherever, as long as it's bleeding, something comes out before the blood gets going. You know what this something is? Bleeding, right?